In this video, you will learn about exponents and their rules, specifically zero and negative exponents. Next, let's review some terminology about exponents. A perfect square is a product of a number and itself. So our examples of perfect squares that we have is we have 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, and 144, because each of these results from multiplying a number by itself. Because, for example, 1 squared is really 1 times 1, 2 squared is 2 times 2, 3 squared is 3 times 3, 4 squared is 4 times 4, and we continue that pattern to get each of these numbers. Additionally, we could keep going beyond 12 squared to have 13 squared, 14 squared, and keep going forever and ever to get all of our possible perfect squares. And these are just some of the examples of them. Next, let's review the terminology associated with powers and exponents. A power is the multiplication of the same factor a specific number of times. And in that, we have two different parts. First, we have the base is the factor being multiplied, and the exponent is the number of times that the factor is multiplied. So what we can see is this whole expression here is the power. The base of this is 2, and the exponent is 4. And what this tells us is we're going to take the 2 and it's multiplied four times because of this 4. Now what we have here are some sample tables of relationships. And what we can see is we have 2 to the 4th power is 16, 2 to the 3rd power is 8, 2 to the 2nd power is 4, and 2 to the 1st is 2. Now besides thinking of it this way, essentially what we're doing is we're dividing by 2 each time. For the 5 to the x, we have 5 to the 4th is 625, 5 to the 3rd is 125, 5 squared is 25, and 5 to the 1st is 5. And to get from 625 to 5, I'm dividing by 5. From 125 to 5, I divide by 5. And from 25 to 5, I divide by 5. And in the last table, I have the tens table, where I have 10 to the 4th power is 10,000, 10 to the 3rd is 1,000, 10 squared is 100, and 10 to the 1st is 10. And to get from 10,000 to 1,000, you divide by 10. And the same thing, to get from here to here, I divide by 10, and from 100 to 10, I divide by 10. Now, if we want to fill in the last box here, what we should see is each of these are something raised to the 0 power. And you'll notice here, the question that this slide is asking us is what happens when 0 is the exponent? Now we can kind of assume that we are going to just continue the pattern. So for my first table, I would divide by 2, and 2 divided by 2 is 1. For the next table, I would divide by 5, and 5 divided by 5 is 1. And my last table, I would divide by 10, and 10 divided by 10 is 1. What we can see here is that for each one of these, the last term when you're raising to the 0 power is 1. So anything raised to a 0 is 1. And that's what our next screen tells us, is that when you have 0 as an exponent, for every non-zero number, a to the 0th power is 1. And we can see that with each of our examples here, I have 5 to the 0 is 1, negative 2 to the 0 is 1, 1.0 to the 0 is 1, and 1/3 to the 0 is 1. So in our simplification of this that we want to make sure we always remember is that any number raised to the 0 power equals 1. Now the next thing we're going to investigate is what happens when there is a negative exponent. Now we're basically just continuing the tables that we had from the previous slide. So what we're doing, if we look at the 2's table, we're going to continue dividing by 2. So 1 divided by 2 gives us a value of 1/2. And 1/2 divided by 2 would give us a value of 1/4. For the 5s, I would divide by 5. So 1 divided by 5 is 1/5. And then if I divide by 5 again, I'm going to get a value of 1/25. For my last table, I'm dividing by 10 every time. So I divide by 10, it becomes 1/10. And I divide by 10 again, it becomes 1/100. Now, if I want to focus on the negative exponents, I'm looking at these bottom two sections of each one of these tables. Now, the first one, we can see it's just 1 over the number. However, the second one is where it's a little harder to see the relationship. But instead of writing this as 1/4, I could write this as 1/2 squared. And instead of writing this 1/25, this could be 1/5 squared. Same thing here, instead of being 1/100, it could be 1/10 squared, because we know that those are equivalent to the 4, the 25, and the 100. Now, similarly, we could do the same thing. Instead of writing, we don't usually write 2 to the first power, but I know this first term could be 1/2 to the first. This could be 1/5 to the first. This could be 1/10 to the first power. So what we're essentially doing that we can see here is I'm taking this number, -1, and I'm bringing it to the bottom. The -2 goes to the bottom. So I'm just kind of taking this number and putting it on the bottom of the fraction. And we're repeating this for all of this. 5 to the 1 goes to the bottom here. And the same thing with the tenths. So I'm taking the number, moving it to the bottom of the fraction, and changing the sign of the exponent to be positive. So in summary, what this rule tells us is that when you have a negative exponent, the a to the -n becomes 1/a to the n. So if I look at our example, I have 6 to the -4. I take this, bring it to the bottom, and make the sign positive. Here, the -8 to the -1, bring it to the bottom, make the sign positive. So whenever you have something like this, you make the exponent positive by bringing it down to the denominator. So whenever we're working with negative exponents, you always want to make the exponent to a positive number. And this is one of those math rules we have to make sure we always follow. So to do this, you're going to rewrite it as a fraction with the base and exponent in the denominator, and then simplify if possible. And just note that the value of a can't be 1. So essentially, what I would do with this first one is if I think this is a over -n, this is really over 1. And since I have this is a -n, I'm going to bring this to the bottom. So it'll become over a to the n with nothing left on the top, so I just have a 1. Now for the next example, again I can make it a fraction, and since I have this negative exponent, I'm going to take this whole thing and bring it to the bottom of the denominator. So it becomes 5 to the second in the bottom. And I have nothing left on the top, so I just write it as 1. Now here I want to simplify this because we know that the 1's going to stay the same. 5 to the second is really 5 times 5, so it becomes 1/25 as our answer in simplest form. In this slide, we're going to go through a couple of different examples dealing with zero and negative exponents. For the first example, I have 4 to the -3. Now, since I have a negative in the exponent, this means I had to bring it to the denominator. Now I can rewrite this as over 1, and since I have this negative number, this whole thing is going to go down to the denominator. So this is going to become over 4 to the third. Since there's nothing left on the top, it's just a 1. Now I can rewrite this as instead of having the to the third, this means it's going to be 4 times itself 3 times. So it will become 1/4 times 4 times 4. And when you plug that in the calculator, when I have 4 times 4 times 4, it'll give us that value of 64. So my answer becomes 1 over 64. For the next example, if I look at my exponent, I have a value of 0. And we know if there's a 0 exponent, always means that it equals 1. So we can automatically assume here, because I have the 0 exponent, the answer here is just 1. For the next example, I have 3 to the negative 4th. Now again, we have this is our negative exponent, and we know whenever we have a negative exponent, if I rewrite this as a fraction, I have to take the whole number with the negative exponent and bring it to the bottom. So this will become 3 to the 4th, and I'm left with just a 1 on top. Now instead of thinking of this as 3 to the 4th, I can think of this as 1 over 3 times 3 times 3 times 3. And when you plug that in your calculator, 3 to the 4th gives us a value of 81. So my answer is 1 over 81. For the next example, I have negative 7 to the 0th power. Now because I have a 0, we know that whenever there's a 0 exponent, automatically means that it equals 1. So since this is 0, I can automatically assume that my answer is just 1. For the next example, I have an exponent of negative 3. Now because this is a negative exponent, if I rewrite this as a fraction, I know I have to bring this whole thing with the negative down to the bottom. So it becomes negative 4 to the 3rd, and I'm left with just a 1 on top. Now I'm going to multiply negative 4 3 times, however I'm going to include the negative 4. This becomes 1 over negative 4 times negative 4 times negative 4. And if I plug negative 4 times negative 4 times negative 4 in the calculator, it gives us negative 64. So this becomes 1 over negative 64, which I can rewrite as negative 1 over 64, showing that the negative just applies to the sign of the number. And in our last example, we have an exponent of negative 1, and we know that this automatically means that I'm going to take this whole thing with the negative and bring it to the bottom. So it would become 7 to the 1st power, and I have just a 1 left on top. Now 7 to the 1st power just becomes 1 over 7. So I'm just writing the 7 one time. And this would give us all of our examples of our different properties of exponents. Now things get a little more complicated when we have to deal with variables. An algebraic expression is written in simplest form when it has only positive exponents. So if there is negative exponents, you're going to switch where they are located, i.e. the numerator or denominator. Write each variable or term in the expression separately, simplify, and then recombine them into one expression. And we'll go through some examples together. So if I want to simplify this first expression, I have 4y and x to the negative 3. Now we are looking for 0 or negative exponents to simplify. And what I can identify is I have a negative 3 exponent, so I have this whole expression that I'm going to simplify. So what will happen is if I write this as over 1, this x to the negative 3 is going to go to the bottom. So it'll become x to the 3rd on the bottom, and I'm left with the remaining 4y is going to stay on the top. So I'll be left with 4y over x to the third, and there is nothing else I can do with those common variables. I have no negative exponents or 0, so I leave my expression as this. And the next expression, again, the first thing we are looking for is 0 or negative exponents. And what I can see here is I have a negative 4 exponent on the bottom. So what I can do is I can take this whole expression here and bring it up to the top. So I have, and I can keep this 1 in front. So I'll be left with a 1. The w to the fourth comes up, and I have nothing left on the bottom, so I assume it's over 1. Now, realistically, if I have this over 1, we know I don't have to write that, and I don't have to write this 1 in front. So it just becomes w to the fourth as your final answer. In the next example, again, we're looking for 0 or negative exponents. And if I look, I can identify that I have a negative 5 exponent, which is attached to the m. So what will happen is if I write this as a fraction, this is going to come to the denominator. So it becomes rewritten as 1m to the fifth, or I could keep it as just m to the fifth, and then on top, the 11 is going to stay in the same place. So it'll be 11 over m to the fifth. I have no more negative or 0 exponents, so this becomes my final answer. In this next example, again, we're going to start by identifying 0 and negative exponents. And what we can see is I have a 0 exponent right here, and we know that whenever we have a 0 exponent, that means that this really is just equal to 1. So if I keep the first part of the expression the same, I have a 3a, and instead of writing b to the 0, I'm going to replace it with 1. And we know this really becomes that it's multiplied. So 3a times 1 gives us our answer is just 3a. In our next example, again, we start by trying to identify negative and 0 exponents. And if I look, I can see that I have a negative exponent with the s to the negative fourth. So I'm going to take this, if I write it over 1, and the s to the negative fourth goes to the bottom. So it'll become s to the positive fourth, and then the 7 and the t squared stays on the top. So it becomes 7 t squared as our final answer. In the next example, again, we start by trying to identify 0 and negative exponents. And I can see that I have a negative exponent with a negative 3. So I'm going to take this negative 3 and bring it to the top and attach it to the already existing 2. So if I think of this as a fraction, the a to the third comes up, the 2 is left in front, and this is really all over 1. Now we know that if something's over 1, I don't actually have to write this, so it gives me my final answer of 2 a to the third. In this next example, we again start by trying to identify 0 and negative exponents. Now in this example, we see we have a negative and a 0 exponent, so I'm going to start by dealing with the negative. If I have this negative 4 I have a to the negative 4, and we know that a negative exponent is always going to go to the bottom. So if I take this a to the negative 4 and bring it to the bottom, it becomes a to the positive 4, and that c to the 0 is left over. So I'm going to leave that on the top. Now the next thing we know is whenever we have a 0 exponent, it means this entire expression is really just equal to 1. So I can get rid of this and I'm going to rewrite it with a 1. So if I continue to simplify, it becomes 1 over, and I'm going to keep the a to the 4th. So your final answer is 1 over a to the 4th. In our last few examples, we are going to be evaluating an expression. So we are going to simplify and then substitute. So the first thing we want to do is simplify the expression. So I have 7m squared t to the negative squared. And we remember that we're looking for negative and 0 exponents. And if I identify, I have a negative exponent with the t to the negative 2. And we know that that means if this is really over 1, I can take this whole expression and move it to the bottom. So it becomes over t squared on the bottom, and we're left with the 7m squared in front. Now, the last thing we have to do is we are now going to substitute and simplify using what's given in the problem. So it tells us that m equals 2 and t equals negative 3. So if I were to substitute here, I can take this 2 and substitute it here. So this part of the expression would become 7 with the number squared, and I'm filling in the value of 2. And then I also see in the bottom, I have a t here, which I can substitute the negative 3 for. So it becomes over that number squared, and I fill in the negative 3. Now, if I simplify this, we know by using our rules that when we're squaring, we're really multiplying it by itself. So this becomes 7 times 2 times 2, and the bottom becomes negative 3 times negative 3. Now 7 times 2 times 2 gives me a value of 28. Negative 3 times negative 3 gives me a value of 9. And we have to check to see if 28 over 9 simplifies, and it doesn't, so this becomes our final answer. So in this example, again, we are going to simplify and then substitute. So we're going to start by simplifying the expression. So if I have n to the negative 3 and w to the 0, and remember we're looking for 0 and negative exponents. We actually have both examples in this type, so we're going to start by dealing with the negative exponent. So I have the negative 3, and we know that we have a negative exponent, which means if it's written as a fraction, this is going to come to the bottom. So it'll become over n to the third, and this w to the 0 is just going to stay on the top. The other thing we know is whenever we have a 0 exponent, like we have here, we know that this means that this really is just equal to 1. So I can rewrite this as 1 over n to the third. Now the last thing we have to do is substitute and simplify using what we're given. So it says n equals negative 2 and w equals 5. So if I'm substituting, I see that on the bottom I have an n. I'm going to replace it with the negative 2. So it'll be 1 over the value of n of negative 2 to the third. So if I rewrite this, it becomes 1 over negative 2 times negative 2 times negative 2. And we plug that in the calculator, it becomes 1 over negative 8, which I rewrite as negative 1 over 8 as my final answer. In our last example, we're going to first simplify the expression. So again, we're looking for negative and 0 exponents. So if I look at the top, I have a negative 1. So this means this whole expression is going to go to the bottom. So it becomes, and I already have in existence this w and this at the bottom. So I can rewrite this n to the 1, and I have the w squared attached, and since there's nothing left on the top, I assume this is a 1. Now, while I can rewrite this as n to the first, we know that whenever anything is written as n to the first, we actually don't even need this. This becomes 1 over n w squared. Now, if I substitute using the n equals negative 2 and w equals 5, 5n equals negative 2 and w equals 5, I know that I can substitute the negative 2 in for n and the 5 in for w. So it becomes 1 over negative 2, and then I have a 5, and it's raised to the second power. So if I rewrite this, it becomes 1 over negative 2 times 5 times 5, which becomes 1 over negative 50 as my final answer.